In this video, we're going to talk about power series. Definition: a power series has the form of an infinite polynomial. Summation n equals 0 to infinity c sub n times x to the power of n. Now plug n equals 0, we get c0 x to the power of 0. X to the power of 0 is 1, so we just get c0. Now plug n equals 1, we get c1 x to the power of 1. Plug n equals 2, we get c2 x to the power of 2, and so on. And the general term is c sub n x to the power of n. This is called a power series in x, where the c sub n's are the coefficients, they're constants, and x is the variable. If we let all the coefficients c sub n be equal to 1 for all n, the power series essentially reduces to a geometric series. So we get summation n equals 0 to infinity x to the power of n, because c sub n is just 1. So we get c0, which is 1, plus c1x, so we get 1 times x plus x squared plus x cubed plus x to the power of n. And this is a geometric series with common ratio, which is x. So we know from what we learned about geometric series that this series converges when absolute value of x is less than 1, and this geometric series diverges when absolute value of x is larger or equal to 1. So equivalently, this geometric series converges where the common ratio, which is x, is between 1 and -1, and diverges when x is larger than 1 or x less than or equal to -1. All right, and larger or equal to 1 here. So in general, a power series centered at x equals a takes the form of an infinite polynomial in powers of x minus a. So we have summation n equals 0 to infinity c sub n times x minus a to the power of n is equal to, plug n equals 0, we get c0. Plug n equals 1, we get c1 times x minus a. Plug n equals 2, we get c2 times x minus a squared, and so on. And a general term is c sub n times x minus a to the power of n. Theorem: given a power series about x equals a, that means the center is x equals a. Summation n equals 0 to infinity c sub n times x minus a to the power of n. There are only 3 cases to consider. Number 1, the series summation n equals 0 to infinity c sub n times x minus a to the power of n converges only at x equals a. In this case, if this series converges only at the center, which is x equals a, then every term will be 0, and the sum of this infinite series would be 0. So this is kind of the useless case, if you will. Case number 2, the series summation n equals 0 to infinity c sub n times x minus a to the power of n converges for all x in minus infinity to infinity. That means for all real x values, this infinite power series converges. All right, case 3. Case 3 is the most important. The power series n equals 0 to infinity c sub n times x minus a to the power of n converges for absolute value of x minus a is less than capital R, and diverges for absolute value of x minus a larger than capital R. R is called the radius of convergence. Definition: the interval of convergence of a power series is x less than a plus r and x larger than a minus r. We get that by solving this expression, this inequality here for x. However, the ratio test does not tell us what happens at the endpoints. X equals a minus r, the left endpoint, and x equals a plus r, the right endpoint. So these endpoints have to be plugged into the power series manually, and we have to plug them in and apply a test of convergence, like the basic comparison test, like the limit comparison test, like the alternating series test, to find out if the power series converges at an endpoint. So let me repeat. The ratio test gives you an interval of convergence but doesn't tell you what happens at the endpoints. The endpoints have to be manually plugged into the power series, and then we have to apply a test of convergence that we have learned before, like the basic comparison test, limit comparison test, or the alternating series test, to determine what happens at an endpoint. All right, let's now look at the interval of convergence diagram. So we know that the power series converges when absolute value of x minus a is less than r. If we solve this, this means x less than a plus r and larger than a minus r. We also know that this power series diverges when absolute value of x minus a is larger than r. That means x larger than a plus r, larger than a right endpoint, or x less than a left endpoint, x less than a minus r. So there are four possibilities for the interval of convergence. Open interval a minus r, comma, a plus r. That means don't include the left endpoint and don't include the right endpoint. And number two, open interval a minus r, comma, a plus r. This means include the right hand point but exclude the left hand point for the interval of convergence. And number three, include the left hand point, which is a minus r. Let me put this back in. And don't include the right hand point, a plus r. And case number four, include both endpoints, the left hand point, the left endpoint, and the right endpoint. So include the a minus r and include a plus r, the left endpoint and the right endpoint. The only way to determine which of these cases we have is to plug in these endpoints into the power series and do a test of convergence to find out what happens at those endpoints. So let's look at an example. Find the radius and interval of convergence for the power series summation n equals 1 to infinity x minus 2 to the power of n divided by n. All right, so what we have is summation n equals 1 to infinity x minus 2 to the power of n. Let me just check from the last page, x minus 2 to the power of n divided by n. We're going to apply the ratio test with the general term a sub n is equal to x minus 2 to the power of n divided by n. So applying the ratio test, we have limit n approaches infinity, absolute value of a sub n plus 1 divided by a sub n. Recall from the ratio test, if this ratio is less than 1, the series converges. So that's how we're going to do this. So let's apply the ratio test. We have limit n approaches infinity, absolute value a sub n plus 1, plug in n plus 1 wherever you see n. So we get x minus 2 to the power of n plus 1 divided by n plus 1, and all divided by a sub n, which is x minus 2 to the power of n divided by n, absolute value. This is equal to limit n approaches infinity, absolute value. Now we're going to flip this fraction because we're dividing by a sub n. So we get x minus 2 to the power of n plus 1 divided by n plus 1 times n divided by x minus 2 to the power of n. Simplifying this, we're going to get limit n approaches infinity, absolute value of x minus 2, because we have the same base, we subtract off the exponents, times n divided by n plus 1. Notice we put the absolute value only on x minus 2 because that's the only part that could potentially be negative. N over n plus 1 is always positive, so we don't need the absolute value on that term. So now taking a limit as n approaches infinity, so we get, let's remove the absolute value term outside the limit, absolute value of x minus 2 times the lim, n approaches infinity, n divided by n plus 1. Divide by the highest power in the denominator, divide by n, and divide by n. And we're going to get absolute value of x minus 2 times limit, n approaches infinity, n divided by n is 1, 1 over 1 plus 1 over n. Take the limit as n approaches infinity, 1 over n will approach 0, of course. So the result is absolute value of x minus 2. All right, by the ratio test, the given series converges if absolute value of x minus 2 is less than 1. or x minus 2 is less than 1, larger than negative 1. Solving for x, we get x less than 3 and larger than 1. And diverges if absolute value of x minus 2 is larger than 1. So that means x minus 2 larger than 1, or x minus 2 less than negative 1. Solving for x, we get x larger than 3. Solving for x, we get x less than negative 1 plus 2, x less than 1. So the radius of convergence, the radius is equal to 1. So now we have to check the endpoints, because the ratio test doesn't tell us what happens at the endpoints. Those points have to be checked manually by plugging them into the power series separately. So check the endpoints x equals 1 and x equals 3. All right, plug x equals 1 into the power series summation n equals 1 to infinity x minus 2 to the power of n divided by n. We obtain, plugging this in, we get summation n equals 1 to infinity. Plug in x equals 1, so we get 1 minus 2 to the power of n divided by n. Simplifying this, we get summation n equals 1 to infinity. 1 minus 2 is negative 1, so we get negative 1 to the n to the power of n divided by n. This is convergent by the alternating series test. Convergent by the alternating series test, we will abbreviate that as the AST. Now let's prove why it's convergent. The general term an is equal to 1 over n is certainly decreasing because we have a constant 1 divided by n, which is increasing. So 1 over n, the ratio decreases as n increases. And the limit of the nth term, limit of an, as n approaches infinity, is equal to limit as n approaches infinity of 1 over n, which is equal to 0. So it satisfies both conditions of the alternating series test, the AST. So therefore, this power series converges at x equals 1. So now let's check the right endpoint, x equals 3. All right, so plug x equals 3 into summation n equals 1 to infinity x minus 2 to the n to the power of n divided by n. So we get summation n equals 1 to infinity 3 minus 2 to the power of n divided by n. We get summation n equals 1 to infinity 3 minus 2 is equal to 1. 1 to the power of n is equal to 1. So we just get summation 1 over n, which is a divergent harmonic series, or equivalently divergent p series with p is equal to 1. Or you can say it's divergent harmonic series. Divergent harmonic series. So now that we have checked the endpoints, we know that we should include x equals 1, because at x equals 1, we had a convergent alternating series, but we should exclude x equals 3, because at x equals 3, we had the divergent harmonic series for the interval of convergence. For the interval of convergence. So here we've drawn a diagram for the interval of convergence of this power series. So when x is between 1 and 3, this power series converges. That means for any value of x in this interval, the power series has a finite sum. That's what we mean by convergence. Because a lot of times the concept of convergence is somewhat abstract. Students will say, okay, what does that mean? Well, what it means is that if you were to plug in any value of x, for example, x equals 2.5 into this power series and added up all the terms, the sum would be finite. If you were to put in a value of x, say bigger than 3, then of course the series is divergent. That means the sum goes to infinity. That's what it means. Or x less than 1, it would be divergent. Now, notice that we included x equals 1 with a solid circle, and we excluded x equals 3 with a hollow circle, because at x equals 1, the power series converged. It was an altering series, convergent series. And at x equals 3, we had a divergent harmonic series. That's why we included the left endpoint, but we excluded the right endpoint, x equals 3, for that interval of convergence. All right, thanks.